All right, when we talk about the climate impact of flying, there's this one number that always seems to pop up. But what if I told you that number is actually hiding the most important part of the story? Today, we're going to do a first principles analysis. We're going to break down the climate impact of aviation right from the ground up. We'll look at the fundamental chemistry, the physics, and the atmospheric science that really define the true cost of a plane ticket. So, let's get right into it.
So here it is. This is that number you see everywhere, 2.5%. The standard line is that, globally, aviation is responsible for about 2.5% of all human-caused CO2 emissions. And when you look at a pie chart of everything contributing to climate change, that slice might not seem all that alarming. But is it really the whole story? I think you know where this is going. As we're about to find out, that simple, clean percentage, well, it masks a reality that is far more complex, and frankly, far more significant. That 2.5% isn't the end of the conversation. It's just the starting point.
So here's our roadmap for today. First, we're going to tackle that 2.5% illusion head-on. Then, we'll dive right into the fundamental science, the nitty-gritty of fuel, physics, and flight. From there, we'll look at why releasing emissions way up at high altitude is a very special kind of problem. And then we'll put all of that knowledge together to calculate the true cost of a flight. And finally, we'll wrap up by looking at why all of this makes aviation what experts call a hard-to-abate challenge.
Okay, so let's start with that illusion. On a planetary scale, percentages can be incredibly deceptive. To really get a handle on the impact, you have to look past the relative figure and really focus on the absolute, raw numbers.
So that 2.5% share, it actually translates to roughly 1 gigaton. That's 1 billion metric tons of CO2 being pumped into our atmosphere by commercial aircraft every single year. Let that sink in for a moment. To give you some perspective, that is more than the entire annual emissions of a major industrial country like Germany or Canada. So here's the key point. While the percentage might sound small, the absolute volume of pollution is just staggering.
So how in the world does aviation generate such a colossal amount of emissions? To really understand that, we need to look at the core science behind it. And it really boils down to two fundamental concepts: the chemistry of burning jet fuel and the physics of energy.
Now, this right here reveals a pretty wild chemical reality that's just mind-bending. Jet fuel is basically a mix of complex hydrocarbons. By weight, about 86% of it is pure carbon. Now, during combustion inside a jet engine, each one of those carbon atoms, which has an atomic mass of 12, grabs and bonds with 2 oxygen atoms that it pulls from the atmosphere. Each of those oxygen atoms has an atomic mass of 16. So you have one carbon atom with a mass of 12 combining with 32 units of atomic mass from the air. The result of this is something called stoichiometric certainty. For every single kilogram of fuel you burn, you create 3.16 kilograms of carbon dioxide. The mass of the emissions is literally more than 3 times the mass of the fuel you started with. It's not magic, it's just chemistry.
The second piece of this puzzle is physics, and specifically this concept of energy density. This is really just a measure of how much punch is packed into a given amount of fuel by mass. Think about it. When your number one engineering challenge is overcoming the incredible force of gravity to keep a 400-ton machine flying at over 900 kilometers per hour, weight is absolutely everything. You need the most possible energy for the least possible mass.
And this is where the sheer scale of that challenge really hits home. On the left, you have jet fuel. It packs an incredible 43 megajoules of energy into every kilogram. Now, on the right, you have our best commercial lithium-ion batteries. They store less than 1 megajoule per kilogram. The difference we're talking about here isn't just large, it's a difference of orders of magnitude.
Let me put it bluntly. Jet fuel is over 40 times more energy dense by mass than our very best batteries. This isn't some small engineering hurdle that we can just solve with a few clever tweaks. It is a fundamental barrier rooted in physics. If you wanted to power a long-haul flight with today's battery technology, the batteries themselves would be so ridiculously heavy that the plane couldn't even get off the ground, let alone carry any passengers or cargo.
So we've established we have an inescapable chemical problem with CO2 and a fundamental physics problem with energy density. But there's a third layer to this, which is an atmospheric science problem. It's not just what you're emitting, but where you emit it. And it turns out pumping exhaust out at 35,000 feet has some unique and very potent consequences.
This whole phenomenon is known as radiative forcing. Essentially, you can think of it as the extra warming caused by all the non-CO2 effects that happen at high altitudes. So, when a jet engine burns fuel, it shoots out hot water vapor into the extremely cold, moist upper atmosphere. This water vapor instantly freezes, forming tiny ice crystals, which we see from the ground as contrails. Now, under certain conditions, these man-made contrails can spread out and hang around for hours, effectively becoming artificial cirrus clouds. And these clouds act like a blanket, trapping heat that's radiating up from the Earth. On top of that, the super high temperature and pressure inside a jet engine also force nitrogen and oxygen from the air to combine, forming nitrogen oxides, or NOx. Up at altitude, these NOx gases kick off chemical reactions that produce ozone, a really potent, short-lived greenhouse gas. The net result of all these complex interactions is additional warming, on top of the CO2.
So, what's the bottom line? After all that complex science, what does it mean in practice? Well, when scientists account for the total warming impact from the contrail-induced clouds and all that atmospheric chemistry, the best current estimate is that you have to multiply the direct CO2 emissions by a factor of roughly 2. The total climate effect of any given flight is about double what you'd calculate from its carbon dioxide emissions alone. This is the high-altitude penalty.
Okay, enough with the theory. Let's put all of this into practice. We're going to apply these principles, the combustion chemistry, those emissions factors, and that all-important radiative forcing multiplier to actually calculate the true climate footprint for a single passenger on one very common international flight.
So for our case study, we're going to look at a round-trip flight from Calgary, Canada, to London in the UK. This is a journey of about 7,000 kilometers each way, so we're talking about a 14,000-kilometer round trip. It's a really typical route for business or a vacation, flown by thousands of people every single week on modern, efficient, wide-body aircraft.
Okay, let's start the calculation with just the CO2. A modern aircraft flying on this route emits roughly 100 grams of CO2 per passenger for every kilometer they fly. So we take our 14,000-kilometer journey and multiply it by 100 grams. That gives us 1.4 million grams, which is 1.4 metric tons of pure CO2, directly attributable to your seat on that one trip.
But as we now know, that's not the whole story, is it? Now we have to apply that high-altitude penalty. So we take that 1.4 tons of CO2 and we double it to account for all those radiative forcing effects. Suddenly, the impact jumps to 2.8 tons of what we call carbon dioxide equivalent, or CO2e. That little e is absolutely crucial. It's a signal that we are now including the warming impacts of all the non-CO2 factors, like the contrails and the NOx chemistry.
But wait, we're still not done. There's one more layer. We also have to account for what are called the well-to-wing emissions. This is the entire carbon footprint of extracting the crude oil from the ground, refining it into jet fuel, and then transporting that fuel to the airport. Life cycle analysis models calculate this whole supply chain, and when we add that final piece, the total footprint for that single round-trip ticket climbs to approximately 3.1 tons of CO2 equivalent.
Now, let's put that 3.1 tons number into some perspective to see if it's a lot. Driving an average gasoline car for an entire year, let's say about 20,000 kilometers, emits roughly 4 tons of CO2. Now think about that for a second. That one 10-day vacation or that one business trip across the Atlantic is responsible for nearly 80% of the emissions of driving your car for 12 full months. It is an unbelievably carbon-intensive activity.
And this really brings us to our conclusion. Based on everything we've just walked through, the chemistry, the physics, the atmospheric science, you can now probably understand why aviation is universally classified as a hard-to-abate sector. The challenges here aren't just economic or political. They are deeply rooted in fundamental science. So let's just recap these core challenges. First, gravity demands a fuel with an almost impossibly high energy density, and batteries just can't come close to competing on a weight basis. Second, even the most promising solutions, like sustainable aviation fuels, or SAFs, face a fundamental issue. Now, while SAFs, whether they're made from biofuels or by synthesizing hydrogen and CO2, can be carbon neutral on a life cycle basis, they are still hydrocarbons. Chemically, they are nearly identical to fossil-based jet fuel. And that means they still produce CO2, water vapor, and NOx right at the tailpipe, which means they still create those same powerful warming effects at high altitude. So this, right here, is the fundamental challenge of sustainable aviation. We started this journey with a deceptively simple number, 2.5%, and we've discovered that the true warming impact is at least double that because of all these high-altitude effects. We've seen that the solution seems to be locked behind the immutable laws of chemistry and physics, that relentless need for an incredibly energy-dense fuel just to overcome gravity. So if our current understanding of chemistry can't deliver a carbon-free, lightweight fuel, it begs a much bigger question. What entirely new breakthrough in physics or materials science will it take to truly solve the problem of flight?